Now I'm gonna delve into the layout and the internal mechanics for that to show you a little bit, the power of TileDB and the flexibility in storing data in any kind of storage medium you may have in mind. So the most important concept here is the tiling. I'm gonna focus on dense arrays. So a space tile, and I'm going to show you what this is the atomic unit of I/O. So we needed to define some kind of an atomic unit of I/O because we can't just slice 1 byte from cloud object stores or even from the disk. We could, it just wouldn't be wise. And also, as I'm going to show you very soon, we apply compression and encryption filters directly on the tiles. So you cannot just have a single tile for the whole array. You need to block it, you need to chunk it, so that each chunk can be self-contained and separate when you access the data. So here's a space tile. These are the extents, like these dashed lines, just to make a point, like what the whole array is 1 tile in this particular case. If we define the whole array as a 1 tile, and if we slice like this, we would fetch the whole array. Because as I said, the tile is the space tile in this case is the atomic unit of I/O. So that would not be wise. But if we define the space tiling smaller, like in this case, then from the disk, from the storage, we would fetch only that tile. So only this light colored blue portion. So tiling is important for fetching fewer data from the disk and therefore increasing performance. But at the same time, the space tiling allows us to lay out the data in different ways, which I'm going to demonstrate. There are 3 parameters that define the layout of the data on the disk. Before I showed you that all the attribute data go in a separate file, right? But I never explained how we sort them on this file and how we chunk them. So for dense arrays, there are 3 parameters that define this order, which we call the global order in our terminology. First, it's the space tile extents. Second, it's the tile order. It can be row major or column major. And then it's the cell order, which can be row major and column major as well. So here are a couple of examples. So in this particular example, we have 2x2 space tiling, and then row major order within the cell. So you see these arrows, row major within the tile, and then row major across the tiles. So these 3 parameters create a space filling curve, which is extremely flexible to manipulate. So you can do this instead. You can say, okay, it's similar to this one, but now the tile order is column major. So it goes like this. You see that the curve follows a different path. Or you may say, I want 4x2 space tiles. So the space tiling affects the order, and then row major across the tiles. In this case, it doesn't matter, but column major across the cells. So you see, with just 3 parameters and the same engine, you can manipulate the order, and the order matters based on your slicing, because the slicing is going to dictate how many tiles you overlap. So how many tiles are going to be fetched from storage. For sparse arrays, it's similar, but here's the idea. We would not be able to do just space tiling because, and then store the non-empty cells in each space tile separately in a tile, because one tile may have had 1 non-empty cell and another one may have had 1,000,000. That imbalance would create problems in parallelization in our case, for compression, for parallel I/O and so on and so forth. We don't like this imbalance. We want the tiles on disk to be of equal size. We want balance there. So we can do that. What can we do? Well, here's what we will do. We will first impose the global order similar to the dense case. 3 parameters: space tile extents, then the tile order and the cell order. Same idea. So the space filling curve is kind of computed. But then we would sort the non-empty cells, and then we would group only the non-empty cells based on a new parameter called capacity. So a 4th parameter for sparse arrays, and we're done. So in this case, it's 2. So we follow the curve and we say, okay, 1, 2, that's a tile. Then we continue, then 1, 2, that's another tile. Then we continue, then 1, 2, that's another tile. And we call this a data tile. And that's the atomic unit of I/O. And if I change, for example, what is it here? The capacity from 2 to 4, you see that the tiles, the data tiles become different. They become larger. So the capacity affects how big the tile is going to be on storage, but also visually. We call these rectangles minimum bounding rectangles. I'm going to revisit this, MBR. And the space tiling and the tile and cell order affect the locality of the non-empty cells, and therefore the shape of this MBR, of this minimum bounding rectangle. And that's important for indexing. But these 4 parameters, again, infinite kind of possibilities in how to lay out your data based on your application. And in follow-up webinars, we're going to show you how we chose these parameters, and actually they come with the ingestors. You don't need to do anything about this. You can configure, but you don't need to overthink about it. We have tuned those for the applications. And one more thing that I want to mention is that sometimes for the sparse arrays, this space tiling, because it's very important, it's very difficult to tune. What if one dimension is string? For strings, we don't even have space tiling. Like, we don't support it. How are we going to chunk? And for floats, how are you going to chunk there based on the granularity and the precision? So it's very, very difficult to define those. You can fine tune them, but it's very difficult to reason about them. And that's why we introduced the Hilbert order. And the Hilbert order looks like this, guys. It's a very powerful space filling curve. And you don't have to think about space tiles. For floats, we bin them, right? We check the domain and we bin the domain based on number of bits we're going to use per dimension. And for strings, we do something similar with the first characters in the string. Again, very powerful. You can check it out. And finally, for tiling, again, the atomic unit of I/O is the tile, and this gets compressed as well. I'm going to tell you how it gets compressed in a bit. TileDB allows for more than one filters. It's not just compression. It's multiple compressors, but also checksums and also encryption. These are all filters. They undergo a very specific code path for computing those on the tile. And this is done on a tile basis. But the actual atomic unit of filtering is the chunk. And the chunk is kind of fixed to the L1 cache size. And this allows us to optimize a lot the way we process the filters and the way we have the L1 cache communicate with RAM so that we minimize these interactions. So effectively what TileDB does is it takes the tile, it chunks it further, and then it passes each of the chunks through a pipeline. It could be, for example, Z-standard compression followed by encryption. And this is done in parallel on multiple threads, right? And this is very, very, very efficient in TileDB. All right, so that's it. I can show you very quickly how the filters work, and actually even compression, just for completeness here. Let's do this. All right, so here's how we create the filter list. So a filter pipeline. Here I'm saying I'm going to use byte shuffle followed by gzip filter, and this pertains to a specific attribute and specific dimension. So you can create them separately. A specific compressor of filter pipeline for one attribute, a different one for another attribute. So it is attached to an attribute. So you can see, again, here the schema. You can see that the filter list has been applied, and nothing else. That's it. I have more information here. I'm going to upload the notebooks for you to see. You can see how to define filters for dimensions and how to use the defaults and all of that. But the one thing that I would like to show you is encryption, because this is quite nice. So the only thing that you need to do is pass a key, a 32-byte key upon array creation. And once you do that, you will not be able to load the array schema anymore. You're going to get an error here. You will not be able to read it at all. You will need the key again. So if you pass the key in the load function, or if you pass the key over here in the open function, you will be able to read the array. So super simple. This is for those that would like encryption at rest.